Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel where we talk about everything I want to, science and math. Y'all should check out my channel sometime. All right, so I don't make any money from it, so it doesn't really profit me for you to like, share, and subscribe, but you could. Okay, so what we're going to be talking about for our new unit is properties and substances and mixtures. And like I told y'all, most of this you already know. It's just a review. So it's not really hard. And what the new stuff is not really hard. It's just long. There's just a lot of it. And I think this might be the biggest one with 13. I don't think there's any bigger than 13. All right. But our very first section is a new concept. And it's a very important concept, so pay close attention to it. And this is the idea. Okay. So here I've got a molecule, and it has bonds here. And so this is, the forces in this are intramolecular. These bonds are intramolecular. They're very, very strong. But you can also have forces between the molecules. See this big old unshared pair on this nitrogen? Well, these poor little oxygens on this water are electron deprived because oxygen is very electronegative. It's going to hog the electrons, and the hydrogens are going to end up with sort of a partial positive charge. And this unshared pair on this ammonia is going to be very attractive, and it's going to want to line up and make a little bit of a bond there. Now, we call them bonds. They are much, much weaker than real bonds. Real bonds, ionic and covalent, are very strong. These are weak but important. There will be no life on this planet. Oh, I don't have two waters. Without water sticking to water. So we'll talk about that when we get to it. So what we're going to talk about is these forces that are in between molecules. So you can see here hydrogen and chlorine being attracted to each other. As one is more electronegative, the other one's more positive, and their opposites attract. All right, intermolecular forces are between the molecules. The atoms, ions, or molecules that hold them together. They're abbreviated IMF, intermolecular force for the cool kids, and there are different kinds that we're going to talk about here, okay? And they affect the physical properties like boiling point, melting point, and we're going to talk about that later in the notes. So going to the first one, which I like its name, it is called London dispersion forces, okay? So these are called LDFs, and you're allowed to abbreviate them, the IMFs and the LDFs on the AP test. And this is, and what I want to do is show you the picture first. Before we look at words, let's look at the pictures. So here we have a little nonpolar molecule, okay? But these electrons are free to fly wherever they want to, randomly. And if randomly a bunch of them fly over to one side of the molecule, that side of the molecule is going to become more negative for just a minute. And then the other side, it lost its electrons, so it's more positive. And that's called an instantaneous temporary dipole. So for just a second, this nonpolar molecule has got a little positive and negative side just out of the randomness of the universe, okay? So here it is with its two sides, and it gets close to a blue nonpolar molecule. And it feels all this negative energy here, and it doesn't like it, and all the negative particles, the electrons will scoot away. They're going to scooch. They're like, ooh, I don't like that, scooch. So now it has a positive and negative side, and its positive side will be a little attracted to the negative side on this one. These are just momentary. They're very, very weak, but they do have just a little bit of random little forces of attraction between molecules that are even non-polar ones. Can you imagine it? Okay, now in words. London dispersion forces occur in all substances. So a lot of times on the AP test, you're told to list all the intermolecular forces present. London, first off, because it's in all of them. London dispersion. I don't know why they're called London. I don't think it's after the city, but I think it's a person, but don't know. Okay, but they are the only type present. They're the only type present in nonpolar. So I'm going to tell y'all NP stands for nonpolar. So we don't have to write this all the time. And P stands for polar. Okay, it's present in nonpolar molecules. They are also the weakest. Everybody has them, but they are the weakest. The weakest. All right. The ability of an atom to form a temporary or induced dipole is known as polarizability. LDFs are stronger when the atom or a molecule has more electrons. Y'all know lowercase e is for electrons. So large molecules will have stronger London dispersion because of the increase in electrons will increase their polarizability. Long, thin molecules have more surface area. So they are more polarizable. Short, round, or branched molecules have less surface area, so they are less polarizable. The presence of double or triple bonds can also increase the strength of London dispersion forces. So that's number one. Number two, we can even number these. See, I think that was one of my problems with my old notes, is they weren't, I feel like those should be numbered, so that you can really get it in your head that these are different. Okay, so number two is dipole. So those were non-polar molecules. So now you got one polar molecule and you got another polar molecule, and the negative side of one will be attracted to the positive side of the other one. Another thing I forgot to tell you is one of the big parts of this unit is we draw a lot of pictures. And how you draw these intermolecular forces is a dashed line. That is the accepted drawing. That means there's a little intermolecular force there. Okay, so for the dipole, they are permanent, so the attractions are stronger than London dispersion. They are stronger. And how it works is that the positive end of one polar molecule is attracted to the negative end of the next one. Okay, number three, hydrogen bonding. Any questions about dipole? Okay, number three, hydrogen bonding. Hydrogen bonding is an intermolecular force that occurs in molecules that have to have hydrogen, and this is just really important, so put little flashes in your head around this. But that hydrogen has to be directly attached to fluorine, oxygen, or nitrogen. So, you see, it spells fun, because hydrogen bonds are fun. They're really, really fun. Okay, now look at the periodic table. Now, I like to say fun, because it sounds like fun. But you can remember it. Remember, just like we can remember our 7 diatomic molecules. There it is, fun. It's got to be these three. So on the AP test, when you're panicking, which ones do hydrogen bonds go to? Know that fluorine is the most electronegative, and then look at what is next to it, ON. And then you remember, oh yeah, hydrogen bonds are really, really fun. They're so fun. Okay, so a lot of times they'll ask you if something's a hydrogen bond or not, and it's got to be attached to F, O, or N. Okay, so then it can also form between molecules. The difference in electronegativity causes a large molecular dipole. And this dipole causes strong attraction to the dipole of the molecule surrounding it. So hydrogen bonding is fun. Okay, so here is what it looks like. So here is oxygen, and hydrogen is attached to oxygen, so that's our qualification. And then this hydrogen is going to get attracted to an unshared pair somewhere. Oh, look at that, unshared pair. That looks great. And do you see how it's the 3 little dots showing the hydrogen bond there. Now, also, it can happen with nitrogen because that's N. So here we've got the hydrogen attached to the nitrogen, so it checks out as being attracted to the unshared pair over here. And then here we also see it with F and N. Okay, how do we feel about that? Feel good about that one? Okay, that one's really important. You should like it a lot. You know how I always tell you should like carbon a lot? You should like hydrogen bonding a lot. There'd be no life on this planet without it. Does anybody know why?
Water sticks to itself.
Water sticks to itself. Why does water have to stick to itself for there to be life on this planet?
Because you can't drink a single water molecule.
True, but there's something more important.
Right?
What am I being?
Man?
I'm being a tree. You ever notice how trees don't have hearts? They don't have circulatory systems, but yet giant redwood trees can get water out of its roots all the way up to its branches to do photosynthesis. And it does it because water sticks to itself, and it's something called capillary action. Did you know this?
Yeah.
The capillary action, it pulls it up through the little phloem, xylem's the food, phloem's the water, right? Pulls it up all the way to the branches, and then you can have photosynthesis. Without photosynthesis, there's no food on this planet, and there's no oxygen. So that's based on it. And then there's lots of other stuff about because water has hydrogen bonding and it sticks to itself, it has a high specific heat. And if it wasn't for that and our world being covered in water, it would be like other planets where during the day it's too hot to support life and at night it's too cold to support life. But because of the high specific heat of water and the fact that our planet is covered in it, and because of hydrogen bonding, we're all alive. We don't freeze to death every night and burn up to death every day. So that's kind of cool, isn't it? The miracle of hydrogen bonding. No life without it. Okay. Never knew to just be so impressed. Okay. Ion dipole forces. So this is our next one. This is number 4. Okay. This force exists between an ion and a polar, I'm writing polar, I should have just put P so we could go faster, molecule. So look at the picture. It's why things dissolve. So you got sodium and chloride. Chloride is negative. The positive side of water will align to it. The negative side of water will align to the sodium. And if sodium and chloride are together, they'll pull them apart. The water pulls it apart. Okay, so this is what I was telling you about, that there is a lot of properties that is because of the intermolecular forces. So melting, boiling, and freezing will, if the intermolecular forces increase, then they increase. So you can think of this like when atoms are stuck together, when molecules are stuck together really hard, they will resist change and they don't want to come apart. They don't want to boil, melt, or freeze. Well, at least boiling and melting, especially, is them coming apart when they're stuck together. The freezing also, like with water, when it freezes, it spreads out. So in the liquid phase, the water wants to be stuck together really, really hard. But then as it gets colder, it spreads out. It doesn't want to spread out. It doesn't want to freeze. Does everybody follow that? Okay, so for the next one. Enthalpy of fusion, vaporization, the energy to melt or boil. As it's stuck together harder, is it going to take more or less energy to get it to boil? More, right? That's going to increase. And we're just talking about the why. We're not writing them. Vapor pressure. So this is the tendency to turn into a gas. If it has really strong intermolecular forces, is it going to want to fly off and be a gas? No. So what's this one going to be? It's going to go down, right? It's going to decrease. Viscosity is thickness. Do you think things that are stuck together more are going to be thicker or thinner, like syrup or like water? It's going to be thicker. It's going to increase because they're stuck together hard. Surface tension, that ability of water to stick to itself, causes almost like a skin, but it's a force that like little bugs can walk on and stuff, is water, whatever it is, intermolecular forces sticking together harder, is that going to cause our surface tension to go up or down? It's going to go up, right? Because it's stuck together harder. So like water, little bugs can walk on it. Even a lizard can. Have y'all ever seen the Jesus lizard who walks on water? You should look at it on YouTube. It's this lizard who runs on his hind 2 feet, not on all four, and he like gets a little bubble of air as he does, and he can run on the water. Anyway, you'll have to look him up. He's interesting. Okay, solubility. Do you think this is going to increase or decrease with greater intermolecular forces? Very good. Y'all are so smart. It's going to decrease because the intermolecular forces are going to be so strong, it's not going to want to let anything else in. You follow that? And then lattice energy. Remember, that's the energy required to turn something into a gas. Is that going to take more or less energy? Definitely more, right? Way up. Okay. So here's an example problem, very typical AP Chem. Is we've got butane and methylpropane. These both have the same number of carbons and hydrogens. They're called isomers, and but they're the same except for their arrangement. Here the carbons are all in a row, and there they're in a T shape. So they told us that butane has a higher boiling point, therefore we know it has higher intermolecular forces. Can we say why? Why do you think butane has more intermolecular forces than 2-methylpropane? Any guess? Okay, so first of all, these are nonpolar. Okay, so that means they got London dispersion, and that's about it. This one's got more surface area. So it's more squishable, and it can make those London dispersion forces better. Does that make sense to you? So therefore, it is more polarizable. And it has stronger intermolecular forces. Okay, this is a very important thing. Really, all three of these, it says, explain terms in intermolecular forces why butane has a slightly higher boiling point. In a way, all three of these are saying the same thing. And so this is really important. On the AP test, you might think you would just write more surface area, but you have to tell them every little thing. There will be things you feel like, well, that's obvious, write it anyway. That's redundant, write it anyway. The people grading your test are gonna have a key. And on that key are 4 things listed. They're looking for those 4 things. Those 4 things might be redundant. You're just trying to project your brain to figure out what's on their key. But they say things that are a little bit redundant. Do y'all see what I'm talking about with this answer? And it's a little bit like, so of course, but you just write it anyway. The more you write, the better you're gonna do at figuring out what that person has on their key. Okay, the London dispersion forces are weakest for which of the following gases under the same temperature and pressure? Explain your choice. So which one of these, hydrogen, oxygen, xenon, or fluorine, think about it this way, would fly off the easiest, be the least bound to its others? Who's flying off? Yes, hydrogen. I heard y'all say it. Why? Because it is what? It's the smallest. Yes. And how you would say on the test, it has the smallest electron cloud. And then you could also say, therefore, it is less polarizable. For the molecule below, identify if the bonds are hydrogen or not. So we're going to write 1, 2, 3, 4, 5. Y'all know that rhyme? 1, 2, 3, 4, 5. Once I caught a fish alive. Did y'all learn that? 6, 7, 8, 9, 10. Then I let him go again. Why did I let him go? Because he bit my finger so. Which finger did he bite? The little one upon the right. How did y'all make it out of preschool, not learning the fish counting song? You learned it? Did you know it? Good education. You learned the fish song. We'll try to make up for the rest. Okay. Number 1. Is that a hydrogen bond? Yes or no?
Yes.
Why do you think it's yes?
Because it's a hydrogen.
Because it's a hydrogen, but is it a hydrogen bond?
Well, it's attached to a bond.
Is it having fun?
Yeah.
No. The hydrogen is not attached to F, O, or N. It is not fun. It is sad. It is not having a party. So number 1 is no. No. The hydrogen has to be on F, O, or N. Y'all, everybody who said yes, do you understand why it's no now? Seeing it? Okay, number 2. Is that a hydrogen bond?
Yes.
Yes. There's a hydrogen attached to an O, cuddled up to an unshared pair. That is a classic hydrogen bond. Okay, number 3. Is that a hydrogen bond? Yes. The hydrogen is attached to the oxygen. So that's the O in fun, and it's cuddled up to an unshared pair. So number 3 is also yes. Okay, how about number 4? No, the hydrogen is not on having fun. He is attached to a C. Okay, number 5, that bond between carbon and oxygen. I say it's pointing to that one. It's a little unclear. Is that a hydrogen bond? No, that's a covalent bond. Okay. Now, if it was talking about, yeah, they've already asked us for 3, so that's got to be what it's talking about. We'll say no, it is covalent. Okay, that was fun. Very typical AP. That whole little thing. That is so AP Chem. All right, properties of solids. Now we are hitting several sections in a row that are just review of honors chem. And some of this we even talked about already in AP in Unit 1 and 2. Okay, so we're gonna give ourselves a little abbreviation. That high is big H, just like on the weather, and low is big L, just like the weather, okay? Due to strong interactions between ions, ionic solids tend to have low vapor pressure, high melting points, and high boiling points. So an ionic solid, think salt. Ionic solid is, sodium chloride. And the positive and the negative are held together by Coulomb's law. We already learned that. They're brittle solids. We already learned that. Due to repulsion of light charges caused when one layer slides across another one, we already talked about that in this class. They conduct electricity only when they are ions are free to move. So that's only when they are dissolved in water or where they're melted. Other than that, salt doesn't conduct electricity, but if it's dissolved, it does, okay? So our next one is covalent network solids. Think diamond. Okay, so there's covalent network solids. Covalent network solids are very strong. Diamonds are strong, aren't they? Covalent bonds, they're formed only from non-metals. Typically, they're hard, strong, high melting points. They do not conduct electricity, except for graphite. That's a little exception. And here are some examples. Diamonds, graphite, silicon dioxide, silicon carbide, boron, nitride. Okay, our next one is molecular solids, covalent compounds. Our example for this, let's say wax. That's a good one, wax. Composed of distinct individual units, covalently bonded molecules attracted to each other through relatively weak intermolecular forces. They can either be polar or nonpolar, so they can all have London dispersion forces, but they can also have dipole-dipole and or hydrogen bonding. They generally are soft and have low melting points. They do not conduct electricity because their valence electrons are tightly held in covalent bonds. Okay, our next one is metallic solid. We'll say a penny is a good example of a metallic solid. The positive cores are surrounded by a sea of moving electrons, cause them to be good conductors of heat and electricity. The close packed positive cores allow metals to be malleable and ductile. You can hammer it into sheets or draw it into thin wires. It's easy to replace one metal with another to make an alloy, just like how we did in lab. So see, all of that was in Unit 2. So easy. All right, examples. So we got a few little examples of things. So this is carbon, hydrogen, and oxygen. So that is a hydrocarbon. It is molecular bonds, a molecular solid. Okay. Silicon dioxide, that is the covalent network. Solid. Magnesium sulfate, that's ionic. Okay. Carbon dioxide is also molecular. Sodium fluoride is ionic. And calcium is metallic. All right, so we did all of that last time. Just look at it again. It says identify the type of each between carbon dioxide. Notice it melts at -78, and silicon dioxide melts at 1,650 degrees Celsius. Identify what they are, and we already said that carbon dioxide is molecular, and silicon dioxide is the covalent network, okay? And then it says, justify the differences. In melting points, we always want to talk about intermolecular forces. CO2 only has London dispersion forces needed to melt, needed to overcome, to melt. Okay, and the silicon dioxide, you are breaking strong covalent bonds. So in the covalent network solids, those are covalent bonds. They're not intermolecular forces. And remember, covalent and ionic are always stronger than IMFs. All right, how we feel so far? Okay, number 3. We've already learned this. You learned this in physical science. Solids, liquids, and gases in 8th grade. Solids have a definite what? Starts with the S, shape, and volume. They do not move freely, they only, starts with a V, vibrate. Can either be crystalline with a shape or what's no shape called? Amorphous. Okay, all right, next, liquids have no, that one's a little weird, so I'll fill it out for you. Definite shape, but do have definite what? Volume. I'm going to just put a big V for volume, right? They can flow and take the shape of their container, and they are very difficult to compress. Gases do not have a definite shape or volume. They are far apart. They spread or diffuse to completely fill the container, and they are easily compressed. So this is the new little AP part to this. AP loves for you to draw little pictures. And so when you draw these little pictures, like here's a picture. The box below represents a closed container with liquid methane, CH4 molecules in the box on the right. Represent the same methane undergoing complete vaporization. So now it's a gas. You're gonna draw these same little molecules randomly in the box, but this is the AP little tricky part. If they give you 5 molecules here, you better draw 5 over there, because otherwise they're gonna count wrong, because what happened to the other molecule? Don't think you've done good enough, so just start drawing them. Make sure you get 5 of them. You can do better than I did. One, two, three, four, five. 1, 2, 3, 4, 5. All right, that's not so hard, is it? AP skill, count the balls, draw that many. Okay, here's another one. We're gonna do solid, liquid, and gas. So I'm gonna draw my solid ice particles like this, just 9 little circles. Really, water when it's ice, it spreads out in hexagons. I don't think we have to get that fancy. So here's my solid, here's gonna be a liquid. We're gonna put them just more random here. One, 2, 3, 4, 5, 6, 7. Okay, there's 8 of them. 9 of them just kind of spread out. And now here's my gas. And I'm gonna draw 1, 2, 3, 4, 5, 6, 8, 9. There they are, nice and spread out. Okay, that's easy. Next, 3.4. Also, another concept you already know from honors. You learned about the ideal gas laws. You learned PV equals nRT. Did you learn the song? Let me think of how it goes. The gas laws are good to know. You can use them everywhere you go. We're talking PV equals nRT. We're talking heavy duty chemistry. I didn't write that song, but I saw the guy who wrote it live in concert. I know you're impressed. When I taught at Pebblebrook, my science department head from the county called me up, and I taught a federally funded class. It was a special class. And he realized that we had a bunch of money we didn't spend, and we had to spend it that day by midnight or we were gonna lose it. And I'm like, I have no idea how we can spend that much money that fast. He says, I know what we can do. We're sending you to the National Science Teacher Conference. So I got sent to New Orleans, and I saw that guy in concert. I also saw, if y'all have ever heard about the Rainbow Lab demonstration, it causes more lawsuits, more people getting hurt, more death than any other chemistry lab. I saw that lab demonstration catch the lecture hall on fire. And when they did it, I thought, I'm never doing that one. They had it all set up on a table, and they bumped the table, and the fire spread up to the ceiling. It was crazy. But anyway, I saw the PV equals nRT guy live and in concert. Okay, it was very exciting. I'm sure it was well worth federal taxpayer money to send me on this trip. I think I learned a lot. I learned the song. Okay, so here's our ideal gas law. PV equals nRT. What does P stand for? What units? Okay, so this is a little bit different. So it's pressure, and remember in honors chem, when you learned this, there were a bunch of different units for pressure. There was atmospheres and millimeters of mercury and a whole bunch of them, right? Pascals. This is one nice thing about the AP test. There's only one unit of pressure, and it is for this, and it will be pressure in atmospheres, okay? V is the volume, and it will be in liters, okay? N is the number of moles, and because we only have one accepted thing, do you remember how there were a bunch of different values for R? There's only one, because they'll be on the AP test, and it's this one, 0.08206, and that is in liters times atmospheres over moles times Kelvin, okay? And now T is temperature in Kelvin, and that is Celsius plus 273. That's another nice thing. Sometimes you see a decimal point with that 273, but it's a whole number. You don't have to worry about the decimal point. Now there's another formula that they love on the AP test. Now, and that is this formula, PM equals DRT. It looks like dirt, but it is using density in the formula, and that is in grams per liter. It is this should be capital M. I don't like it that these notes make it look like a lowercase m. Capital M is molarity, lowercase m is molality. It is molarity, and molarity. Oh, that's not here. Oops, forget that. I messed up. I'm getting ahead of myself. I'm getting righteously indignant over something before I'm supposed to. This is little m. This is the molar mass in grams per mole. Okay, all right, so here is an example problem. It says, calculate the molar mass. So I'm going to put MM question mark. I always annotate my problems so I can get rid of the words and just have the numbers. Of a gas, if 22.6 grams, that's a mass, of the gas is stored in a 55-liter tank, that's a volume, exerts a pressure, so that's the pressure, of 0.23 atmospheres at a constant temperature of 35.5 Celsius, but I know right off the bat that I need to turn that into Kelvin. So I'm going to do that right off the bat. Actually, she filled it in there. Somebody do that on your calculator. Tell us what it is. 273 plus 35.5. It's going to be 300 and what? Who's got their calculator?
308.5.
308?
Yeah.
Point what?
0.5.
35? 0.5. I see it. All right, there we go. There's our Kelvin. You don't put degree marks on Kelvin. All right, so now we're going to use the PM equals dirt, okay? So always write your formula down because they require you to show your work on the AP test. If you don't show work, they don't give you any credit. One way to show some work is just writing the formula down. Just copy down the right formula and you got it. Then show the numbers you fill into it. So the pressure is 0.23. Now on the AP test, you should include all the units, but I think I'm going to just do it without right now because I want to hurry. Times M, because that's what I'm solving for, the molar mass, little mm. So equals the molarity, the density, which is grams per liter. So that's 22.6 grams over 55 liters. So that's my density. Times the constant here, we'll draw it up there, which is 0.08206 times our 308.5. So we multiply these together, divide that one out, divide by 0.23, and the molar mass equals 45 grams per mole. When you get your answer, put a box around it so the grader could quickly see that you did it right and not be wasting time looking for your answer because they'll get annoyed and just not give you the credit. Now make it clear. All right. Another one you learned in honors, Dalton's law of partial pressures. If you have little pressures of gas, they add up. Remember that one? So this is how you can collect a gas. Here we have a test tube with a reaction going on. We put it in like a plastic bin full of water. You put a container full of water in the plastic bin and then run a tube up under here. It'll bubble up, and as the gas comes in, it will push the water out, and then you can stopper it, and you've got a container full of that gas. Okay. So when I used before block schedule, we would do that in honors and AP, but I really have not done it since then. Always run out of time, but maybe we can try to get that in. All right, so here is a partial pressure example. We want the pressure of oxygen, and we have the pressure here, 726.0, and we have the pressure of the water we need to take away from it, and the pressure of just the oxygen is 740.9, and this one has millimeters of mercury. I think on the real AP test it would be atmospheres. All right, so this is something new. All of that was, you already know, right? That was all easy stuff. You remember those gas laws, Dalton's law. Okay, this is something new. It's called mole fraction. Did anybody learn it in honors? I don't teach it in honors. Did Ms. Corn? No, good. It's good to learn something new, right? The percentage of a partial gas in a gas mixture is the mole fraction. You can also multiply the mole fraction by the total pressure to get the partial pressure of a specific gas. So the mole fraction is the part divided by the whole. Okay, or you could get the pressure of a certain gas if you do the mole fraction times the total. So here is an example problem. What is, if a mixture is 3 moles of oxygen and 4 moles of hydrogen, what is the mole fraction of oxygen? So the mole fraction of oxygen is the oxygen 3 divided by the whole thing, 3 plus 4, or 7, and that's 0.43. Put a box around it. And that does not have units because it is like a percent. Okay, because you know you can write percents as decimals. Okay, what is the partial pressure of oxygen if the total pressure is 2 atmospheres? So the pressure of oxygen, we can get that is, where did we get that from? 0.4. Oh, we take our mole fraction, which is 0.43 times 2.0, because it's 2 atmospheres, equals 0.86, and this time it's atmospheres. That one we have a pressure. It's not a percent, it's a pressure. Okay? Are you okay with that one new thing we've learned so far? Intermolecular forces and this. That's all we've learned new so far. All right, number 5, except we learned about drawing pictures. Kinetic molecular theory. Oh, something else you already know. Remember learning this? I have a great little video made in the 80s in Canada about this. It's a cartoon, it's so funny. I don't think we'll have time to watch it, but it's great. Okay, gas particles are constantly, what goes in here? Moving. I told you already knew this. Moving. Collisions are, in an ideal situation, the collisions are perfectly what? Starts with an E. Elastic. Gas particles have negligible volume. And are there attractive forces with an ideal gas? No, there are no attractive or repulsive forces. And the average kinetic energy is proportional to the Kelvin temperature. Okay, we remembered all that. Okay, that's all. This formula, you learned it in physics, you learned it in physical science. Okay, but this is the new thing. Okay, yay, something new. Okay, it's this little diagram of it. Okay, so at a given temperature, the molecules of gases have the same average kinetic energy. Does every single molecule, are they all going at the same speed? No, it's the average. So we can do a little graph of it. So here's the number of molecules and the molecular energy, and the average is right there. That's what the temperature is going to be, but or there, depending on like if you heat it up and stuff. Most probable is under there, but there's the average. That's it. I said it backwards. Okay, so here's our little curve. This the highest part is the most probable, but the average is right there. And if it gets hotter, then more molecules have more energy and more of them go over this way. But also notice it flattens out. as it gets hotter. So this is usually a problem where you have to draw it. They'll draw this one and say, this is oxygen at 25 degrees. What would the curve look like if you heated it up to 1,000 degrees and you draw a little curve like that? Does that make sense to you? How do you feel about that? Notice that the peak is not at 1,000, it's back some, because that's the most probable is not the same thing as the average. Okay, note that the most probable velocity increases as temperature increases. Also, the curve begins to flatten out, indicating a larger number of molecules are moving at a greater speed. So they like that one. That's a good one. That's a good AP question. However, since molecules of different gases will have different masses, at the same temperature, the molecules of different gases have different speeds. Okay, so there are two terms you need to know: diffusion, which is a gas spreading out, and effusion, which is a gas going through a little hole. Why do we care about effusion? Effusion is real important. Like putting a gas through a little hole is used a lot in manufacturing. It makes them get colder. Gases get colder when they go through a little hole. So this is our experiment. Everybody hold out your hand. Everybody make your mouth real big and breathe in your hand. Notice the temperature of the gas. Now, as you're breathing out, make your lips into a little bitty hole and notice what happens to the temperature. Do you feel it get colder? Isn't that cool? Little experiment. If you didn't feel it, do it again. Make the hole smaller and you'll feel it get cold. All right, so the rate of effusion through a small hole and the rate of diffusion spread out are related to the masses of the particle. The rate of effusion and diffusion increase as the mass decreases. Smaller ones move faster. Or the rate of effusion and diffusion decrease as particle size increases. Okay, so here we've got 4 Maxwell-Boltzmann distribution curves. So one of these is for 4 noble gases: helium, neon, argon, and xenon. One of these is going faster than the others. Do you think the fast one, the blue one, is the helium or the xenon? The big one or the little one? The little one. So this is helium, this is xenon, and then so this one is the middle one, argon, and then neon. So all that. So that's a very AP question, to put these in order and then say why. They would love something like that on the test. My neon leaked kind of bad. Okay. Let's go to number 6. We are not halfway through. How's our time? Oh, so this is the unit that's just so long. Okay, but we already know this. This page you already know. Ideal gases. Gases behave ideally under high temperature or under low temperature. Which one is it? High temperature, yes. Because if they're low, they slow down and they end up sticking together, right? Like condensing. And are they ideal under high pressure or low pressure? Low pressure. Because if they're under high pressure, they're squished together and they're more likely to interact. Now, and if in the ideal gas law, we say that there are no intermolecular forces between the gas particles. Now, of course, in real life, they can have intermolecular particles, especially if it's low temperature and high pressure. Okay? Gases no longer behave ideally when they have low temperatures and high pressures. That's what I just said. At low temperatures, the particles are moving slowly, so they can start having attractions. They end up colliding with the walls of the container, and they decrease the pressure. Okay. They contain less and decrease the pressure. Okay. Under high pressure, the gas particles push closer together. When the particles are closer together, they form intermolecular forces, IMFs, which slows down collisions and decreases the pressure. Also, high pressure, when the particles are pushed closer together, this makes the volume of the gas molecules become significant. You know, big V is volume. See, that's what that's saying. Okay, now here's an example problem. Argon deviates more from ideal at extremely high pressures than neon does. Which of the following is the reason for the difference? Is it because the particle volume of argon is greater than that of neon? Yes, it is. It's bigger, it's got a bigger volume, it's more polarizable, it can start having more interactions. Okay, number 2. Under which of the following conditions of temperature and pressure will hydrogen be expected to behave most like ideal? High temperature, low pressure, right? So that's C. Highest temperature, lowest pressure. Okay, number 7. Solutions and mixtures. This is where I was being righteously indignant. I was not there yet. This should be the big M. Molarity is big M. Moles divided by liters. Okay, so this again is something you learned already in honors. A solution is a homogeneous mixture that can be composed of solid, liquids, or gases. Molarity is moles divided by liters. The solute is the substance that gets dissolved. The solvent is what does the dissolving. I remember that because I draw a V for solvent, and then I put water in it. Well, that's kind of purple water. I put purple Kool-Aid in it. Some purple liquid. All right, so that's how I remember this. Everybody remember that from honors? Oh, yay, we're about to learn something new. Okay, so, here's the example molarity problem. Approximately what mass, so that's what I'm looking for, is the mass of copper sulfate that's hydrate, and this is its molar mass, 250 grams per mole, is required to prepare 250 milliliters, that's a volume, of 0.1 molar, that's a concentration. Do y'all remember square brackets stand for concentration? Did you learn that? We'll write it right here. Square brackets equal concentration. Okay, all right. So, for our molarity, 0.1 is our molarity, is equal to moles divided by liters, and when this is milliliters, it needs to be in liters, so that's 0.250 liters. 0.250 liters. All right, so now do that little math, and 0.02 grams per mole times 0.0250. Oh, I did that wrong. 250 grams per mole. And we get 6.25 grams. So with these molarity problems, sometimes you just have to divide moles by liters and you get your molarity. This time they didn't ask for the molarity. They wanted the mass, so I had to get the moles. So I solved for moles, and then I converted moles to grams using the molar mass. Did y'all follow it? Okay. All right, here's our new fun thing. Okay, so this is the dilution, the famous dilution equation. That if you are going to change a concentration, you have a certain molarity, and then you have a certain volume, and you want a new molarity or a new volume. How much water do you have to add? What do you have to do? Okay, do this. So that's M1 V1 equals M2 V2. Dilutions are solutions prepared by adding water to diluting more concentrated one. For example, you've got of your volume 1, 200 milliliters of a concentration 1, 0.6 molar. So these should be our big M's. Make these big M's too. These are not little M's. These should be big M's. Okay. All right. Is added to 400 milliliters of distilled water. So volume 2 is going to be equal to 400 plus 200, which is equal to 600. Does that make sense to everybody? While we did that, that's our new milliliters. Okay. And now, what is the concentration of the resulting solution? So we want the concentration, we want M2. Now, notice that what we're adding is magnesium chloride, but what they're asking for is just the concentration of the ions. Everybody followed that? That's important. Okay, so we write down our little thing. M1 V1 equals M2 V2. We substitute in. So I'm going to try to do that kind of. So this is 0.6 times 200 equals M2 times 600. So you just multiply these together, then divide by 600, and the answer is 0.20. Is big M would be your units, equals M2. Okay, but they didn't, that is the concentration of magnesium chloride. But they didn't ask for magnesium chloride, they just asked for magnesium. So what you have to do is you have to look at the ratio. And then every magnesium chloride, for every magnesium chloride, for every one magnesium chloride, there is one magnesium 2 ion. Do you see how there's one magnesium per magnesium chloride? So this is a 1-to-1 ratio. So the answer is the same. It's 0.20 molar. We could put little concentration things around. However, if they had asked for the chloride, it would not be 2.00. What would it be? It wouldn't be 2. If they had asked for the chloride, what would it be?
Oh, it would be 0.4.
Yes, it'd be 0.4. Why?
Because it's twice as much.
Because there's twice as much. The ratio would have been 1 to 2. Did y'all understand that? Do you need me to say it again? Because this is going to be on the AP test. I can guarantee it. Y'all want to hear it one more time? That they will do this fun little thing. One reason why it's fun is, did you notice how we didn't have to change this out of milliliters? We didn't have to change it to liters. We could just use, as long as the units are the same on both sides, we don't have to change it because it's a ratio. And the units will cancel each other out. So that's one thing fun about it. M1 V1 equals M2 V2. That's a very easy equation to remember. You just plug it in, simple little algebra. We love it. But they have to make it complicated. So they're going to, instead of asking something simple, they will always make you look and see the ratio of the ions. And there's one magnesium for every 2 chlorides. So you have to look at, once you get the concentration for V2 or whatever it's going to be, then you've got to think about this ratio. How many chlorides do you have in every magnesium chloride? Well, you have 2, so you have to multiply it by 2. And we'll practice this more, but just know that that's a thing. All right, next part's easy. Okay, so this is showing you how to do it. You weigh it out, you dissolve it in some water, distilled water. You put a little bit in your volumetric flask. You add some distilled water to get every little molecule out of the beaker, and then you fill it up to the bottom of the meniscus. The bottom of the curve is on the little scratch mark on the line. Okay, and this is what I just said. With the chlorines and stuff, it says, okay, so you got sodium, make sodium and chloride. It's 1-to-1. But calcium chloride is 1-to-2. Because of this, 1 molar solution of calcium chloride will contain 1 mole of calcium ions, but 2 moles of chloride ions. So we will have twice the molarity of the solution. Okay. So here's the example problem. What's the concentration of chlorine in a solution made by dissolving 10 grams of zinc chloride in a solution that has a final volume of 500 milliliters? We could take our grams of zinc chloride, we could change it to moles. Its molar mass is 136.3 grams per 1 mole. And then to find out the chloride, because there's 2 for every 1, there's 2 moles for every 1. So we do our little math and we get it equals to, I'm gonna write it up there, 0.147 moles of chlorine ions. Now, if they wanted the concentration, so molarity is equal to the moles per liter, 0.147 moles divided by 0.5 liters. So my concentration, square brackets, is 0.29 is its molarity. Doop, doop. How'd you feel about that one? That's a very typical little problem. You're just using that definition and you're looking at the ratio. Okay, 3.8. Representations of solutions. So, particulate diagrams are used to represent interactions between components of mixtures and to represent concentration. Use your little brackets to mean concentration. The main thing to consider is that anions are generally larger than cations, that you need to show the correct number and the orientation. This is more about these little drawings. Between ions and solvent particles, you have to have the correct number of particles based on concentration. They will make you draw little pictures. If the solvent and solute attractions are strong, a solution will not form. So this is what I was telling you about. There are rules whether or not things dissolve or not. I teach it to honors. We use the little acronym thing, NAGSAG. I'm not sure if y'all have to know it in this unit or not. I don't remember. You have to know it eventually. But if it is, I'll teach it to you. I'll pass it out and I'll explain that in more detail of how you know it. Because it's not in detail in this note, so I'm not sure if it's in this unit or not. Okay, so here's an example. Here is calcium ion. We got water. We want to show how they would be attracted to it. Is it going to be the Mickey Mouse's head or ears that are going to be attracted to the calcium? His head, right? Because that's the oxygen that has the higher electronegativity. So you draw some on there, make sure you got the headway. Ta-da. Okay, solubility. So this also is something from honors. So much of this is honors. Here's the vocabulary you learned about. Highly soluble, it will dissolve. slightly or sparingly soluble, only a small amount will dissolve. If it's insoluble, it can't dissolve. You remember these vocabulary words from honors? If it's miscible, what will it do? It will mix. It almost sounds like it's saying mixable, but it's miscible. Immiscible, it cannot mix. And an aqueous solution is in what? What does aqueous mean? Water, that's right, it is water. Okay, so there are some things that are mixable. Okay, so the rule is like dissolves like. That means polar things like water can dissolve polar things like salt. Non-polar things like gasoline can dissolve non-polar things like Sharpie. Okay. So like dissolves like is the rule. It works. However, on the AP test, they will not let you say like dissolves like. They have to say, you have to say why. You have to talk about the intermolecular forces. Okay, so you're not allowed to talk about that. Substances with similar intermolecular forces to the solvent will dissolve, but substances with intermolecular forces that are different from the solvent are unlikely to dissolve. So this tells you the answer on the AP test, but this is what you write down. Like dissolves like. So, okay, we're not going to talk about the intermolecular forces because I want to hurry. This is sodium chloride. Is it going to dissolve better in water, which is polar, or hexane, which is not? Water or oil is how we can think about it. Does salt dissolve better in water or oil? Water. Okay. This is y'all don't need to know the name. Okay, this is an organic compound that's got this OH hydrogen bond. Do you think it will dissolve in water? Do hydrogen bonds like water?
Yeah.
Yes. So it is also going to go into water because it's got a hydrogen bond. That one doesn't have any hydrogen bonds. It is non-polar. So what's it going to dissolve in? Hexane. This is like our oil. Carbon dioxide. It has London dispersion. It is non-polar, so what's it going to dissolve in? Hexane. We can get carbon dioxide to dissolve in water in soda pop, but it has to be under extreme pressure, doesn't it? And it doesn't take long for that soda pop to go flat once you open it, right? Okay, potassium chloride, that's ionic, so what's it going to dissolve in? Water. And we're not going to worry about the last one. It's a little bit more organic chemistry than you know. And I'm not sure that you have to know. Okay, separation techniques. This is just some lab stuff. Sometimes you use filter paper in a funnel, and that's to get a solid out of a liquid. Okay. Evaporation, if something has been dissolved, you can evaporate it and the water will go away and it will leave whatever you dissolved in it behind. Has anybody ever done that with salt water and let it all evaporate and seen the salt crystals? Okay, recrystallization is where you can separate a solid from a solution if there is a large difference in solubility. At different temperatures. It's also used a lot of times to purify stuff. P-U-R-I, that is really messy. That says purify. Okay, distillation uses differences in boiling point to separate things. So you got a mixture, you heat it up, one boils off, you run it under cool water, it condenses, and you can get it over here. And so I bought this stuff last year for AP to do a lab where we do this making essential oils. And we ran out of time, but I still got the stuff, so maybe we can do it. If we do it, we'll do it after the AP exam while we got a few weeks extra. And we'll do our projects, but we might can do some fun labs too. All right. don't know why we ran out of time. Okay, here's another one that's called extraction. You put a polar layer and a non-polar layer, and the whatever you're trying to get will go into one of them, and you use this separatory funnel, and you let out just one layer, and now you've separated them. So it has to do with them being used the two immiscible layers. You use oil and water or hexane and water or something like that. And then chromatography, we did paper chromatography, and it's the different IMFs that you use to separate them. Now, this goes into further detail of chromatography, because they used to always ask questions on this even year before last on the AP test. But on the Facebook thing, they said that they don't think it's going to be on there this year, but we better learn it just in case. So chromatography, what makes it go is the stronger something is attracted to the solvent, the further it moves. Okay? And it's called being mobile, the mobile phase. And then the part that doesn't move is called the stationary phase. The component that travels the farthest distance has the strongest attraction to the solvent, and the other one has the weakest. All right. Now, thin layer chromatography. It took me a long time to figure out I wanted to be a teacher. I was smart in science and math and made good grades. I was going to use it to get rich. So I started out where I was going to be a physical therapist. You only go 3 years of school, and you can make as much as a doctor for grad school. The reason why is because doctors pay so much in malpractice insurance. Physical therapy is safer, less malpractice, so you can take home the same amount of money with less education. At least that's how it was in the 90s when I was in grad school for physical therapy. To get into grad school for physical therapy, I did a turn at a hospital in a lab, and we used thin layer chromatography. It is this is something extremely polar, and it pushes through that way. So we did that a lot. So then I was in grad school for physical therapy, and I realized I hated it. I could not go to work every day and hurt people. You have to hurt people in medicine. When I worked in the hospital, I had to draw blood. Nobody's happy to see you at 5 o'clock in the morning when you come in to see them in the hospital with your needles. And then in the physical therapy, you make people exercise till they cry. I really started hating it. And so my mom was like, well, you've had all that science and math. Why don't you become a teacher? And I'm like, a teacher? I am not going to get rich. But I love my job, so it's okay. But physical therapy, you can make a lot more money if you can, or being a doctor, if you can handle hurting people. All right, column chromatography is how it's normally done. My son Nathan, who is getting his PhD in chemistry at Georgia Tech, he does this every day. Instead of sucking the solvent up through the medium, it's these little columns, and you push it from the top down, and it separates. How fast it goes down is how much attraction it has to the solvent, and he uses it to separate things out to see what he made so he can test it and see if he made something new, which he often does. He's making brand new things in science. Okay, so it has to do with, once again, with polarity, and the one that travels the slowest is one level, and the least polar will go the fastest. And it is used, just like I said, for separation. So he does this, tests it, figures out if he made a new chemical, and if it was the chemical he was trying to make. All right, spectroscopy and the electromagnetic spectrum. This is another one you already learned in honors, so I'm going to talk about it real quick, and then we're going to stop. So the electromagnetic spectrum is light, but it's not just visible light, it's all of them. The whole radio, microwave, and how I remember is Ronald McDonald is very ugly, extra gross. radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. They all are created by the sun and other stars. They all travel at the speed of light. As you get closer to gamma rays, it has more energy and the wavelengths are more frequent. Okay, so it's the whole thing. They all has different variables. The variables is frequency, that's the symbol for frequency, wavelength, that's the symbol for wavelength, and energy are the variables. Light is in little packages called photons. Okay, so do y'all remember that from honors? Microwaves is the one that is lowest in energy, and this is the part you have to know for AP. Microwaves only cause molecules to rotate. So sometimes they ask that. What do microwaves do? Everybody think rotate, okay? Infrared is higher. Infrared is heat. And it has less energy than visible. And slide this up. Okay, and what it does is cause them to vibrate. Okay. Ultraviolet, it will cause things to move up. It causes our little Bohr model electrons to hop up. So it causes it to go in an excited state. Okay. And it starts off on the ground state. So this was our flame test lab. And then the extra energy is emitted as light or other parts of the spectrum. Okay, we are going to stop right there and get ready to go. So part 2 tomorrow, but it's only a little bit.